try to build it in Haskell from scratch and see how it compares with regex. So we're just trying to compare and contrast the differences, see what the advantages and disadvantages are. The thing about this is it's actually regex. We're not using C bindings or anything like that. This is actually real Haskell. And we see up here there's kind of like a little bit of a joke thing that actually spills out regular expressions if you pass it. Okay. Let's see. So does everyone know what regular expressions are? Okay. I'll just give a quick refresher just so that we know, like, I'll explain the things that I care about amongst here. So, if we want to match an A, that's the regular expression that we use. Just an A. It's pretty straightforward. If you want A and a B, this may seem redundant, but it will make sense later on. If you want A and then a B, you just concatenate them together. A or B, you just put a pipe character between them. And an optional A, this always succeeds. So no matter what happens, an empty string is always going to match any string, even if it's an empty string. A star also always succeeds. It will greedily try to grab as many A's as it possibly can. A plus, this can fail because empty string is not considered one of the options. And here we have selected we have 3 A's to 5 A's, so that range. And A-N is the choice of A, B, C, all the way up to S. Single digit, this is shorthand for a digit. Backslash W is alphanumeric.
You're going too fast.
Keep up.
Key stuck on the yeah, key is stuck on the thing. And you're fighting against it. Oh, yeah, yeah.
What do you want? Actually, let's just take it out. Oh, I don't need it. Here we go.
Oh, it's still.
Yeah, but this is all pretty straightforward. It's just, so this is just classes of characters that we're interested in. So digits, alphanumeric spaces, and the dot is any character. So I'm sure you all know this stuff, but it's just to clarify what stuff I'm going to cover. I'm actually going to cover more stuff in this thing. So this is how we're going to represent a parser in Haskell. So the type looks pretty gnarly, but essentially all it is a wrapper for a function. And the function says, so the function says, I take an S, which is your input, and you have a choice of either it's going to fail with some error messages, that's the string, or it's going to be successful and return the thing that you care about and the rest of the string you haven't passed, right? So, so here's an example. So you've got A, B, C, D, E, F. If we want to match on the first, it always matches from the leftmost character. So if we match on an A, we're successful, we get an A back, and the rest of the string that we don't know anything about, right? That gets passed on to the next guy. And here's what happens if it doesn't match. So there you two choices: match, you don't match. And here the A doesn't match the X over there. So we put a message up there, and the message can be used. Right, to make this useful, we're going to need some functions. So one of the functions here is it's called symbol. It's just a name on it. Basically, what it means is we're going to create a new parser. Given a character, it will match on a character. So if we, so the whole point of this is we want to create a parser, which is repeat the string char, and we're going to look at the S, which is our input string, case match on it, and if there's a match between the first character and the character we passed in, we're good, right? We have a match. So it's going to return right, the character character and the rest of the string. Does that make sense? If it doesn't match any other situation, empty string or the character just doesn't match, then it's just no match for the character. I mean, again, the message is irrelevant, so whatever you want to do. So here's an example. One thing I skipped over was P is just shorthand. It's just a way to peel out the function. So you've got this construct with P, but I don't care about the P. I just care about the S in the string. So here it passes this, pulls out the A, gives you BCD back. And again, no match on this one, right? Because X doesn't match it. Very, very simple stuff. Or that a 3 in this case was a 3 matches. So the next step is we're going to create a functor instance. So this is steadily going to get a little harder and harder as we go along until everyone leaves the room. So this is a way of changing that A. And why would you ever want to do that? So basically it says, I've got a function from A to B, and I want to change this A to a B. So why would you do that? Well, the reason might be, let's say you passed a digit, which we saw in the previous slide, right here. Wouldn't it be nice to turn that into an integer, right? Something useful, instead of a character or something. Or maybe we want to get the next instance from the A, so B. So functor enables you to go inside a parser, tweak it a little bit, give you a new parser back. Right, so what we've got here is, this is our parser. We peel off the P because we don't care about it. And what we're doing is creating a new parser here while running the old parser and then just tweaking this thing. So we don't care about it. If you've got an error message, let the error go through. But we do care if it's successful.
You're building you would parse that for every kind of regular expression thing, classification thing.
Let's just see how it goes.
So can I ask a question?
Sure, yeah, absolutely.
Which example of B, A and B you can have? Like A could be like a character, but
yeah.
You mentioned like an integer, or
yes.
What else?
It could be, let's say I want to double up the string and create a tuple, no problem. Or repeat it 5 times, do whatever you like. It'll become clear later on,
okay.
Useful ones. I mean, obviously, putting in a tuple is like, why would you do that? But reading, creating an integer out of some digits, that's useful. That's like, okay, we can do something with that. Because if we read some digits, and we know they're digits, well, it should be an integer, right? It should be convertible to an integer. And now we've got types. The thing about regular expressions is, there's no types. It's a string. You're passing a string. This is where Haskell gives you a slight advantage because you have types. Okay, so, so I have a stupid example, which is we're going to match on, forget this F map, we're just going to match on A, so get an A back. But I reach inside that parser and say, got the A back, I'm going to tweak it and jump it up one to B. So it goes to A, B. So I put C in here, and this was a C, you get D. And there's nothing left, right? I'm only matching on A, there's nothing left to pass after that. So here's another function. This does nothing. ID. It's a function that goes from A to A. Doesn't do anything. Sometimes those things don't look interesting, but they're actually really, really powerful. And just to show you that the functor instance doesn't do anything in the case of an error without no match. So it's not doing anything different. All we're doing is saying, if it's successful, you can make a change to it. This sort of leads up. So this is, I'm going to prefix with just, you heard about data maybe, right? maybe is it just or nothing? So I've just put a just in front of it. And we'll see why that makes sense later on. Right, so we've already handled the first case, which is match a single character. Now what we're going to do is mention A, then a B. It's not A and B, but it's A, then a B. So this is the dreaded monad that everyone fears, right? And we'll see how it goes. So the whole point of this is, the whole point of a monad, but okay, the point of this is, I've got two monads, two passes, not two monads, two passes, and I want to jam them together to get the properties of both, right? So the thing I care about is, I run a passer for A, then I run a passer for B, and I'll pull the A out, pull the B out. That's what a monad enables you to do. I'm not going to go into too much detail on this, but I'll just show you the result of that. So what it enables you to do is now get syntactic sugar for this stuff. You get do syntax, which means I can run P1, and let's say that's sim A, right? And I can run P2, and it shoves the A in there, and let's say it was sim B, it'll shove the B in there and return the list. So you don't really, once you've got it in a parser, you can always pull that A out, which is all you care about, right? You want to pass the, like here, here's a classic example, right? So I want to match on A, and then I want to match on B. So it finds this one, jams it together, and then leaves the rest of it as a string.
The question is the test one, like the name of the new parser that you were talking about?
Yeah, this is now, exactly, good point. This is a new parser. Very good point. So the whole thing, everything is about, like, if I have a monad, if I have a whole bunch of parsers, what I really want to do is crunch those parsers together, right? So I've got 5 parsers, okay? Well, I know how to combine 2, great. I've got 3 left. I know how to combine another one, keep combining them. So you end up with whatever you want. So this describes how you can lift a value, a pure value, into combine 2 parsers together. So once you combine 2 parsers together, you can combine n parsers together. And what it does is, just to show you that there's sort of a relationship between these two things, this is syntactic sugar for this. It's exactly the same thing. So all it's doing is, here's my parser, there's my operator, and then there's a function from A or X, because it's just named, to a new parser. And it just repeats itself. Don't worry too much about understanding the complete details. If you know it, great, but if you don't, just the idea is, all the monad is giving us here is this syntactic sugar, a way of combining parsers together. Because all we had at the moment was like, oh, I know how to pass an A, great. I know how to pass a B, but what about A and a B? Right, okay, so next. And just what it also gives us is shorthand for this. So you know the map function, right? It just like runs through a list, right? So if I map over this, if I use map in, which is this monadic source, you can now look, instead of saying sim A and then sim B, you just have ABC, and it just does it all for you. So it's a nice short. And the thing to realize is, all of the stuff that I'm telling you about, once you learn this, you can apply this to anything in Haskell. Once you learn regx, it doesn't apply to anything, right? It's regx, right? It's its own DSL, which is like very good at what it does, but it's limited. With Haskell, the whole thing flows through everything. Anything useful is probably going to be a functor, probably going to be an applicative, probably going to be a monad, and now you can do stuff with it. You don't actually have to understand it. You just have to know that now you can combine stuff.
I have a really quick question. I don't know much Haskell at all. So ABC there, so are strings in Haskell character strings then?
Yes.
Yeah, I just wanted to verify I was right on that. I figured it once, but.
It's a good point. String means list of child. Right. Yeah, so it's a list. Yeah, I was going to put that on the slide, but yeah, so that's list of child, but it's not supposed to.
Thank you.
Yep, no problem. Right, so now the next one is A or B. We're getting close to something useful. Just bear with me. Like, dude, really? A or B? So now I'm going to introduce another type called alternative. So this says, again, same thing as a monad, but instead what we've got is two parsers. We're going to jam them together as an OR. So it says, try the first one. If that fails, try the second one. I don't really care if that fails, but you know, this gives you options. Now the monad is like A, then B. If like either of those fails, you're out, right? So this is extremely useful. So again, you've got two parsers, and you create a new parser that wraps the whole thing around, right? And it says, run the first parser, that's P1. If it fails, try P2. If it's successful, stop, we're good, right? So the whole point is we're going, it's left biased, and we're going for success.
So one question, could you have done that with the monad where you say pull the X if it's left to the Y?
No, you couldn't because the definition of the monad says, I'm not even going to bother, so you go back. Yeah, if you see here, it says, I'm not even going to try, I'm just out, right, you're dead. But I can show you how we can do that with optional. So that's the question mark thing. So that you get that actually.
So you basically lose all that information.
Yeah, it's gone. It short circuits the whole thing. So you could have this long thing that says, you know, try to go for an A, then a B, then a C, then a D, then an E, and the B fails. Everything's dead, right? So you don't have to say, well, if it's successful or whatever. Okay. So here's an example. This is try A, and we're done, right? Doesn't have to go any further. Right, because A matches the first character, so we're good. The next one says try A. Oops, didn't work. Let's try B. And this one says, oops, nothing at all. So try A, try B, and then a fail. Okay, so we're going to do 3 because we're doing so well here. This is cool. So this is the first one is the optional one. So that's once we created that alternative instance, we get these things for free. So I'm going to explain how this works. So we kind of saw this before where I said I did fmap just on a parser. So we're going to do this, fmap just, but then if it fails, it becomes nothing. So a nothing parser, so it's going to return a nothing. Does that make sense? People look confused.
Just those 2 words, a little bit, what they're doing, what they mean.
Yeah. So the thing about this is, we were saying like if we match on an A, we want to try to match on an A, right? But what happens if it fails? We want to have some way out. And what this does is this gives us an out. It says, well, try to match on an A. If it does match on an A, you get just it. You're done, right? But if it fails, return nothing. So it's a parser that has nothing, nothing, THING in it. So now you can do things like, Carlos, like you were saying, can I check within a monad? Yes, you can. If you prefix it with optional, you can case match. You can say, is it just? Is it nothing? These ones are a little tricky to understand, but again, this stuff is for free. I don't actually have to create any code for this. This just comes with alternative. But I put the code in here just to show that I'm not hiding anything. So it's a recursive definition. Basically, what it says is, what it first of all does is this is applicative notation. It's just so much nicer. But anyway, you run the parser, so it has to run. This is sum plus. Run the parser, then try to run this many times. So it loops around, trying, but it expects at least one success. This one doesn't care. It's like 30 different fails. I don't this will always succeed. This guy could fail. Don't worry about the details too much of that. It's a little mind-bending because it's like, you know, anything recursive, you're going to like sit there, try to look around a few times. So this is where Haskell shines. So we're going to use do some error handling. There's not really any real error handling in regex. But what this does is you're going to add a combinator, and what it does is it takes a parser and the error string and puts the error message in there. So you get a little bit more context, but it only applies if it fails. I mean, if it's successful, there's no error message? It doesn't make any sense. So again, have a parser and create a new parser with just a little extra effect. And what it says is, if I get an error, then I prefix it with the error message. Okay. And if it's successful, fine, I already get it. So we'll see that in use. Yeah, so just to show you, oops, we failed, this is how you use it. It matches W, no problem, so there's no reason for an error message. What happens if it doesn't match? Oops, we failed. And then now we're going to do the regex classes. So that's how you do regex for digits. It's cool, right? With the knowledge that we have so far, that's how you do it in Haskell. Oh my God, it sucks, right? So, yeah, check the 0, check the 1, check the 2, 3, 4, all the way up to 1. Find if one of those matches, then you have a digit, right? That's not good. So we need one more construct. So we have the symbol takes a chart. Let's change that, tweak that just a little bit. So what you end up with is a predicate that says, you do the same sort of thing, case match on that, create a new parser. And what it does is it calls the function that says, tell me, is this true or not? Is this valid, will this pass? If it's valid, then you put the first character in there and get the rest of it. Otherwise, it's not match. So let me show you what that looks like. So we get the same functionality by doing this. Because what we're saying here is the character you pass, that first character, does it match A? If it does, we're in business. And so these are important. So we'll throw sim A away. Right? We're moving up in the world. This construct, psim, is basically the building block for the whole thing. So, so let me show you something more interesting. So that's what it would look like in Haskell. So this is a predicate that says, check the character is a digit. And it turns out that works out really well. This is just part of the data.child library based on and this matches on the space, as you would expect. Alphanumeric is a little tricky. You have to say it's an alphanumeric or it's an underscore. Right? So that's just the way they decided to do it. And dot says, I don't care what it is, it's always true. Right? So that will always be successful, except in the case of an empty string. So it will match on any character. And if we want to match on A through N, that's how you would do it. So you can kind of, if you sort of, squint, you can kind of see that some of the stuff looks very similar. Const true just says whatever happens to const true, and it's very similar. But the cool thing about this is the vocabulary of regex is very limited. There's no certain things you can do. There's XHD, W, it's there's some class stuff like XDigit and stuff like that, and upper, lower, and that sort of thing. But we can create anything we want. We may have a different vocabulary that we care about, like octals. Can't do that in regex.
Can I say a question?
Yes, absolutely.
So, where are atoms coming from? From the char library? Atom?
Oh yes, this is actually prelude. That's prelude.
Into prelude. Okay,
Yeah, that's
so
in prelude.
Cool atom with the database.
Oh yeah. So this is enum.
I will get back like a function from char group.
Oh right. So elm says I have a list. It takes a value and a list of the same type of value and gives you back a loop. So for example, in the specific case, this one, it takes a char and a list of chars, and it says, check the first one, check the second one, third, fourth, all the way to the end. If any of those match, then return true.
So you're carrying that, right?
I'm what?
Curry.
Oh, yeah, well, okay. No, not currying, just error reducing it. So if I was to write this out properly, because I'm so lazy, it's like \c, and then I'd say C, ln A to M. The reason why I didn't do that is because it's redundant. It's sort of, the C doesn't give you any more information, right? It doesn't tell you. You're holding onto a variable name, and you're like, this can only be an error at some point if I get it wrong, right? But if you have two variables, right, you don't want to. Yeah, sorry. I should have spelled that out actually.
You're using a little backtick so it becomes an infix.
Exactly, infix operator. Yeah. So, and that's the cool thing. You can do weird stuff like you can push this up on the left-hand side. Yeah. It's okay. Right. So let's do something pragmatic, something real. So this is an IPv4 address, and here it is in regex. Looks pretty good. You've got pulls out a bunch of digits, a dot, a bunch of digits, a dot, a bunch of digits, and very concise, very nice, right? Yeah, right. Oh, that's not so good, right? It's nice, right? But just hold that. So okay. So what I've done here is I'm creating a data type, abstract data type, which holds the 4 integers. So this in no way is safe. This is still characters that come back, string. But nevertheless, so this is 4 integers. So we'll only accept integers. And this is the long-winded way of writing this out using do notation, where you say, let me explain this. This is, if you remember psim digit, is give me a digit back, right? And sum says 1 or more digits. So it just grabs as many digits as it possibly can. And then the read is just a way of converting that to an integer. It's just a, so you get a number out of it. And here what we do is we run this parser, because this again is just a parser. I went inside it and changed the digits into an int, pulls out this one, looks for a dot, pulls out the next one, looks for a dot, and then just jams them all together into there. You'll see there's a lot of stuff that we can do to trim this whole thing down. I'm just like, from the knowledge that we have, this is what we can do.
So since you're not pulling anything out of the dot, it just ignores it?
Yeah, I just chose to ignore it. I could keep it, but there's no point. It's just a dot. So it still passes it. It's just we don't care about it for the output because it's not relevant. We only care about the numbers. This is sort of a shorthand for it. It's kind of like how I would do it. It just kind of squints, for some people who don't understand, but you can kind of see what's going on. Anything after the dollar, it just says, this one, this one, this one, this one. And there's just this little tweaky thing where if I don't have an angle bracket, it just ignores this guy. The angle bracket here, it's, after a while you get used to this. It's just syntax, right? But it just means it's a lot sort of easier. And you've got no variable names. If things got a little more complex, I wouldn't do this, I would just do it this way. But the thing about this is, I put A and then A again, right? Or I got the order wrong. This, you can't get the order wrong. It just puts it all in the right places. So names are not useful. There's more errors to check. Okay, so that was great. We did IP address, right? Well, it turns out it's not valid. So that's a requirement. And this is what happens, is you start off with a regex and it's like, oh, yeah, this is kind of cool. And it's like short, concise. But it never quite works. There's always some little tweak you do later on, you're like, damn, I can hack something together to make it work, or we can do a prompt, right? So 0 to 25 without a leading 0. That's what it looks like in regex, just the one thing. And it kind of makes sense. What we're doing here is we're trying matching on the widest number possible. So taking 3 digits, it's 250 to 255, no leading 0, that's the key. 200 to 249, 100 to 199, and then what we've got here, 10 to 99, and then 0 to 9. That's what you have to do, right? So, so let's be real. This is what it's going to look like. Oh, crap. Can you just change something for me? Like, I want that third octet just like tweaked a little bit. It's like, oh, I don't want to do it. Okay, so in order to be able to do this properly, we need a function. So that's the beauty of this. Regex is done. There's a fixed vocabulary. There's only so much you can really do with it. What we can do is we can always add combinators. So I'm going to add this combinator here. What it says is, the essence is, I'm only going to accept numbers between 0 and 255 with no leading 0. Right? So how do you do that? Well, this classic one, which is pull out all the digits, just grab all the digits, and then check to see if the length is greater than 1 and there's a 0 in the head, then we've got a leading 0 in our hands. Right? So 0 is okay, this is, it's a length of 1, but this is length greater than 1. So oops, leading 0. Then it checks the range of our 0 to 255, and if it's not in range, give you an error message. Does that make sense?
So out of curiosity,
sure.
I've had ignorant about Haskell. You said that there's a way to take a bunch of a string of characters that are a bunch of digits and turn that into a Haskell integer.
Yes. Yeah.
Could you theoretically also write this by just matching as many integers as you can, trying to convert it to an integer, and then just handling the error if it fails?
Well, the thing is, if you're matching the integers or the digits, you know it's an integer, right? That's not, you're not going to get an error message because any, obviously overflow or something like that. But
does it treat leading zeros? So it ignores leading zeros?
Oh, yeah, that's fine. It does that. Yeah, sorry. That's your question. Yeah, it will ignore leading. So that's true. In a lot of languages, that's not the case. It sees the leading 0 and it's like maybe it thinks it's an octet or just crashes because it's like that's not a number or something. So yeah.
So head x should be head x, right?
Oh, sorry, was it?
Head x should be head xx. Is that right?
This one?
Down the head there.
The
After the end head.
If length greater than 1,
Yeah.
Oh, yeah.
Head x stats, right?
Yeah, sorry. Yeah, you're absolutely right. Wow, good spot. Yeah, I just.
Debugging is easier from here on account.
Yeah, I know. And the thing is, I went through this like several times and I thought, I keep finding errors. It's like, damn, okay, so I keep changing it, tweaking it, but yeah, no, good spot. Wow. Okay, points for anyone who.
Yeah.
It's awesome. Does that make sense? So, and here, this is the read where it's just Haskell syntax to say convert it, in this case, to an integer. Right? So I'll get 0, 4, 4, 4, 4, 4, press an integer value. Yeah.
So it seems like this is also going about parsing it in a fundamentally different way. The regex did this in a very string-oriented way, and this will still parse an invalid IP before and then filter out that numbers.
Well, I haven't actually got to that part yet, but in a way, if you remember the monad structure, it will never get into IP. It will never actually get in there if it was invalid.
Right. It's just it's not doing it in a character-based way.
It's doing it character. It's definitely a character-based way because everything is based on piece. Everything I'm doing, which is character by character by character, it's the only way it can work. So if you look at this, psim is the core thing, element in this thing. So we look at here, this guy here, it only handles a character at a time. Every time you call page 7. Some will say, oh, I'll run the parser many, many times, right, to actually go through the thing, but it's still only, it's doing everything a character at a time.
All I mean is that the regex version will never, well, I guess it never actually converts data, whereas the Haskell version will convert things that are out of range into an int before it can filter.
Yeah, exactly. In that case, and then let's see. So yes, okay. So yeah, this is huge. Let's say it's like 5 million, right? It will read it, but the thing about it is it's lazy, so it may not actually do it. So in this case here, it says, oh, you're out of range. So even though I said there's a let statement up here, nothing is pulling it. Nothing is saying, I want that in. It's only at this point. Since this never happened, since it never got to here, this statement doesn't happen. It's very pure. So it's a lazy language, so it only does what it needs to do. So it never actually reads the value, because this is just an assignment. It's saying in is the equivalent of read excess. It's not doing anything.
But to do the comparator, it has to do with it has to.
No, for n, yeah, but n is not mentioned. And n is the read. N is only mentioned down here.
In the comparator.
Oh, sorry, you're right. Yeah, sorry. No, quite right, yeah. So whatever I said, just ignore it. Yeah.
So, yeah, 5 million is a 7-digit number, so it would actually be in all those digits.
Yeah.
Okay. Yeah. Versus, I am just contrasting this with my question, which would get to that, actually failing 5.
Well,
5, 0, 0. It would fail on after running out 3 digits.
Yeah, the thing is, okay, so here's the thing. I could have rewritten this differently. That's not a problem. I could have said, okay, I'm only going to allow between 1 and 3, and we have some code, I think it's later on, which will say, which adds a little extra stuff to it, and it says, width has to be 1 to 3, and this. The problem was that it becomes a little more complex, and I wanted to keep the code simple. I have this in there, but I also have this a more generic thing. And in fact, the more generic thing is what this guy gets called by this guy. I don't use this code. This is more just show you just how it kind of works. Right? But I will show you the code later on. So anyway, this will work. This will give us 0 to 255, and we called it octet. And it looks the same. We haven't really changed anything. But what we can do is use this syntax. It's exactly the same. All we're doing is changing NN to octet. It's just a name. Right? And the octet is that width from 0 to 255. Or use another combinator, something that I wrote, just to show that you can really make this concise. And this is actually difficult to do in regex. What you actually have to do is read the first thing, then repeatedly read the dot and the integer 3 times, right, to get the IP address. Whereas this says, you might be able to kind of see what's going on. It's run the octet 4 times with dots in between. 3 dots, 4 numbers.
You actually don't have to do the first. You can just do the octet and then you call it by a dot or an instruction. You don't have to do You don't have to do the once and then
yeah, but the or means that you've got possibility of something wrong. Well, we're getting into this sort of like. Okay, so here's another slightly more real thing, which is I want to figure out what the 20-bit block is. So anything in this IP address range. So you can see here it's between 172, 16 to 31, and there's octet and non-octet, right? So that's what it looks like. It's a bit long-winded, but you can kind of see what's going on. Range 172 to 172, 16 to 31, 0 to 255, or make it a little simpler. We know it's 172. There's no range, there's no change. This is the only one that's kind of odd, and we just reuse octet. So this applicative syntax is, it's not that difficult. It's just like, you just kind of squint, look, ignore the, each of these is still a parser. And it just says, run this one, run that one, run this one, this one, this one, this one, this one, done. Does that make sense? How many people got lost?
So it's still going character by character though, right? So it's
Yeah.
First read 1, and then 17,
Yes.
and then 177.
Yeah, that's syntactic sugar for yes. It was map in sim and then 172, so it says, okay, sim 1, okay, cool. Sim 7, sim 2.
So it will fail quickly.
It'll fail as soon as it can.
As
I
soon
mean,
as it can.
Yeah. So for example, well,
I'm just expanding to the situation where grabbing things that
I can do these sort of, I can do some of these online, but let's just go to the next bit. Oh yeah, so this is sort of similar. This is really explicitly find me stuff with a width of I to j. Right? That's very, so the way that this is a bit tricky to look at, but again, once you write this comment, you don't have to deal with it. You just, a library writer will provide you all of the functions that you need, and you just got to leverage them. So width then says, well, find me something within a certain range. This is actually reflecting the regex thing, which says anything, the number of A's, I A's to J A's. And you can if you kind of squint, it says, we know we have to have at least I A's, right? That's just a given. Has to at least have that. So that's what this is. It basically replicates the parser I times. Because you've got to do sim A, let's say it's 5 times. Sim A, then sim A, then sim A, then sim A, sim A, sim A, 5 times. And then it says between 5 and 7. Then we're going to do this. Many Z becomes 2 times, 7 minus 5. And then there's this hairy stuff that you kind of saw before with the sum and many. There's just a slight variation on that where it's limited. So instead of infinite, it's limited by width. But don't worry about this too much. Again, the details aren't important. So if we want to match this, we want to match between 3 and 5 letters, then we'll use the regex or the Haskell version. So they're very, very similar. There's more, obviously the Haskell one has more characters in it. So this is something that you can't easily do in Haskell, in regex, is recursion. So I want to check that the parentheses are balanced. I didn't think you could actually do it, but it turns out on the web, I was looking around, it's like, oh, you can do it. It took me a while to find a regex interpreter that would actually handle it. But this works, apparently. It only works for one set of nested parentheses to see if they're balanced. That means that open paren, closed paren, like any number of parens in between. I tried, like naively trying to do this in many, and I was like, whoa. What about the stack and some weird stuff?
One of the definitions of being a regular language is that you can't do that arbitrarily.
Yeah.
What parser is that, or what regex engine is that designed?
I think it was PC-RE or something like that, but it's like, who cares? Tell me, I'd like you to make a change to this, right? I mean, you don't want to touch it. Did you have a question?
Yeah, I just wanted to also say that this is not a regular language, but what this is using is the backtracking feature that you might for a regular expression.
Yeah, but I mean, you're right, but there isn't such a, in order for this to be useful, you're going to have interesting little things like \R or, the backtracker things and stuff. But, right, anyway, so that's that. This is how you do it in Haskell. Very concise. So it says, match the open paren, match the closed paren, and do this repeatedly inside of it. And this is just an extra thing I'm just saying, make sure that we've reached the end of the string. right? So in Nazi, it's like $1, right, in regex. Backslash C, yeah, exactly. Yeah.
Dollar is at the bottom.
Yeah, but it depends if you set it for lines or yeah, whatever. I mean, the thing is, there's so many flavors of it that you know. This is another example. This is the parentheses, but just a little bit of extra stuff to make it a little more interesting, where it actually tells you the depth of each paren that you're going down. Anyway, that's kind of useless. This is useful comment between. This will come up a lot. So what this means is you have an open delimiter and a closed delimiter and the thing that you're after. So what it might mean is like this here, square parentheses. You're going to have, you want to find all the stuff inside the square parentheses, right? All inside the quotes. So this will do that. And what it says is, you look for that opening delimiter, run it. I don't care about it. I don't really want it. Run this parser and then run the close parser and return it. So, and this is how you do it in applicable syntax. Really nice. So I don't care about the L, I don't care about the C, I just care about that guy. Very result. Again, these are combinated so you can you write it, you're done. So here's an example of how you use it. So you're looking for a quote, double quote, as a starting thing, and an ending double quote, and then any number of characters in between, just as long as it's not a double quote. Right? So that's, does that make sense? Okay. Between brackets, this is between square brackets. Here's your open bracket, here's a closed bracket, everything but the closed bracket. So, you know, and the thing is, in reality, you probably wouldn't use this. This is more of a library function, but these are useful functions. Let's do something even more useful. So this is Apache log format. So here's something off the web. This is one line from a Apache sample. Then, and so here's the IP address. Here's a date in square brackets. So leading up to that, there's the statement that was used, the get, and it's quoted. Some integers, quotes. But if you notice, everything is delimited by a space or spaces, right? So there's always a space between each token, essentially. And so what we're going to do is pass that. We've already done this guy. The IP address, it's done. We handled that for IPv4. This one's a bit tricky, and I'll show you the code just, oh yeah, before I do, we're going to put all of this junk into here. So this is the IP address, this is the time, the string is this guy here, the quoted string, a few integers, and 2 more quoted strings. And I'm going to cheat on this one because dates are just really, really hard. And to validate them, use date package, right? I mean, so there's something called data.time, pass time, and you give it a complex formula that then they will, you know, which takes a little bit of time to try and figure out which is it, you know, D, B, Y, H, M, S, and there's a time set. And so in order to pass the date, just the date component, we're going to use between brackets, so that's between square brackets. It pulls out the data, and remember it just drops the parentheses, the brackets on either side. And then we're going to run this guy right here. And if it fails, we'll give a nice message. If this one fails, we'll give a nice message. Again, that's not important. You know, the details of this. So this is the slide that's going to give you guys the most grief. But I'm not going to edit. So what we're going to do here is we pass the IP address, which we already have the code for. So we're going to reuse that. We're also a dash. We've handled that. That's just a dash. Another dash, and then we pass the log date, which we just saw before. Quoted. We handled that. is, I probably didn't describe that, but that's just essentially some piece is digit, right? Many digits, or some digits. And all of this stuff is done. And the sort of the trick to this is, as I mentioned before, is each of these tokens is separated by space. So I'm just overriding the definition of hash to say, so here's your angle bracket hash, and what it does is it says, run, see this is to the left, and this is to the right, if you want it like that. So it says run the first one, so run IP address, pull it out, ditch the spaces, and then run the second. And this part is just like, whoops, we're missing spaces. So looks for the spaces, gets rid of them, and then runs the second one. Again, you don't have to know that, but the cool thing about this, syntax is really easy. We've had those spaces.
This problem would become harder if you wanted to be more tolerant of log messages formatted quite quickly. Like instead of those 3 integers, throw in 2 of them. Yeah, I mean, you want to do something with that. You still want to consume that log message, but
yeah, but the thing is, whenever you're doing stuff like that, you're aware of what the tolerance is. You know, like you have to know what it is. You can't handle everything, but you have to know what the give and take is. Otherwise, it's soup, right? I mean, you could say, okay, I don't really care. Just give me. You could pass it once and say, just give me integers that are in that somewhere, right? You pull each one out, right? But you still need the variance. You need something to go on. So this doesn't preclude that. It just means you probably have some or statements, right? And we've defined that. So, oh yeah, and just to attack this, remember IPv4 regex? That was just the first part. We hadn't even got to the date or the quoted strings and stuff like that. So, so anyway, regex didn't help us out a lot. Just a couple of the very useful combinators, just to tell you that they exist, is not. Not's always useful. It's just like I'm looking for something that is not a digit, right? And this will do that. So what it does is it says, if you remember, optional means that a parser will never fail. If the parser runs, like let's say we want to match on a digit, and the letter that we have is actually the string that we have is an A. It's not a digit. It's still, we pass it, and we want to have a nothing pass it. So it never fails, really. It just creates a nothing with the rest of the string. So, so what this does is it says run the parser. If it's a nothing, it's good. So everything's upside down, right? If it's good, then it's bad.
it's also be required.
Well, it's, yeah, I mean, it's not, right? It's the exact opposite. So good is bad, bad is good, up is down, you know. So just a little summary of this, is what we have so far. So if you remember, this is the construct we use to match on a single layer. If we want A and B, just use A and B, so that it looks pretty good. A or B. This is what I was talking about Filippo before, was a passes are actually numbers. No reaction, okay, good. So this is checks A or B. This is using the alternative instance. A or an empty string, meaning will always be successful, is this. So it will never fail. Many we store, some we store. So this is the regex, this is the Haskell equivalent. So it's not too bad. I mean, definitely the regex is a little more precise. But the thing is, there's a lot of stuff that we can do you can't do with regex. A through N. So if we want to check for an X digit, that's what you use this class to call out X digits. we're going to call it underscore H, but it's this guy. I just named it right now. Single digit is underscore D, which is semi-integer. Single space. Right, and then now we've got some cool stuff. So there's some things that I can tell you about, which is the opposite stuff. So it's not a digit, it's not P or F. Then you use this, which is not P, and make sure there's a character in it. Becomes very, very cool. You want to do the same thing for \capital W, \S. Right, now we need to do some testing. So we're going to use quick check. I don't know if you guys know about quick check. So, and I'll give you an interactive example. So, what we want to do is quick check enables you to do testing where it will generate random data, and then you can see if that data passes your tests, expected tests. So in this case here, we're going to create valid data. So this replicate we saw before, where I'm going to choose numbers between 0 and 255, because that's what an IP address is, get 4 of them, and put dots in between them. So that should be a valid IP address. So if it fails our parser, then we know we've got something wrong. And then I'm going to run the quick check stuff. So it's going to run this parser and explain. If it fails, then it will give you an error message. So,
Can you increase the text size?
what's that?
Can you make the text larger?
Local screen with the text.
Yeah, how do I do that? Oh, yeah. I mean, just got this computer, so
I think you were ready.
oh, okay. Like 24 or something.
Go big.
You see that? Okay, we'll make it really big. Let's go.
2,000. I want to see 2 letters. And pounds.
Yeah, I really hard.
Okay, cool. So, so what I did here was like you can there's a quick check thing that says I created a random generator to generate those IP addresses, and this is some sample ones that came out of it. And so what we can do is
Drag it all the way up to the top, it'll maximize.
okay, so that's boring. It actually passes the tests, but let's tweak this a little bit. So what we're going to do is we're going to change this a little bit and make it between 0 and 256 instead of 5. Oops, pause out of range, found a 256. So this is a good way to kind of test stuff en masse, just like pile stuff at it. As long as you can create the generator you set. So let's see. I'm running 500 times. Yeah. But it actually gives us a lot of information. And it turns out to answer your question, yeah, so I have something called pause restricted, which says, you can see this, where you specify the minimum, max, and the width to really tighten it up. But again, I just wanted to, so there's a lot more code involved in this, but So, but here's some cool stuff. So, quick check, you need to check functors. I mean, Haskell is a very powerful language because it's driven by actual laws, and we created a functor instance, but we want to check that it's actually valid. It's actually easy to do this stuff and find out, oops, it was actually wrong all the time. So we can run quick check instead. We can also run quick check on monad laws. It turns out that it's just category laws. And category theory just says, it's not much to it. It's really, there's an identity, and that you have the identity. If you put the identity on the left side of a parser or on the right side of a parser, it doesn't change anything, right? It's also associated, meaning that if I have 3 parsers, I can put the brackets anywhere I like, nothing changes. And then there's the alternative laws. The only reason I'm running this is because I screwed up on one of these. The monad instance that I had was actually wrong. And I was like absolutely convinced that, yeah, just write this stuff. It's easy. And I realized, oh shit. So now I'm paranoid. Anytime I do a monad, I make sure it supports the laws. And it's very interesting that some situations that are very trivial, there's no monad for it. Or the monad is really complex to actually do. Anyway, so I'll just show you some of the advantages. So error handling, this is something you just don't get with regex. We can extend the language. So regex is fixed. There's only so many combinators you can really use. It's composable. It not only works on strings, but in tokens, which is really, really cool, because it means you can actually have strongly typed tokens. So you run Alexa to create the tokens that you need, and then you can actually use a parser to actually pull the stuff together correctly. And there's probably, for more complex situations, you probably want to do some lexing and then run a parser against it. Testable using quick check properties. I think I pulled that stuff up. It's present support for recursive parsing, and that's either impossible or difficult to do at regex. And we get to reuse Haskell concepts, so it means that once you understand this stuff, it applies to everything. And the first thing I do is, when I look at a package that I'm interested in, is what are the functors, what are the applicatives, what are the monads? Because some of the libraries have nothing useful until you get to those. And parser is a number, which oh yeah, before I do this, this is just kind of a fun thing. So I found this on the web. It's binary trees and strings. So this is, I don't know if you can kind of see this, but the idea is that you can write a string, and that's the left branch and that's the right branch. So like here, you've got the left branch is the 231, the right branch is the 65. And this is the code that you need will work, and we'll put it in this structure. Very, very concise. Again, very tricky. I'm not sure how that would be done in regex, but even if you could do it, the point is about this is it's very composable. You can actually, once you've got a parser for IP addresses, you're done, right? Once you've got one for a cache log there, you reuse them. You don't have any reuse with regex. Regex is, you write it once, you pray to God you never have to touch it again, and if you do have to touch it, it's like, oh crap, I broke something, especially back references, right? Because you start to add a grouping on the left-hand side and you choose all the references. I'm assuming. Right, so, again, do you want to see an example of this, or should we go to numbers? Or you guys starting to sink lower, yeah, let's crank it up. Answer is number. Well, it is. Okay, but so there's something called a number instance for Haskell. This is how you write it. And I was playing around with this stuff, and it looks pretty close to a number. So the requirement is, I mean, in technical speak is, plus has to be commutative, a monoid, commutative monoid, and multiplication has to be a monoid. Right? Meaning that it has to have a sort of a zero element. So multiplication for numbers, the zero element is 1, because if we multiply anything by 1 on the left side or the right side, it's the same number. If you do addition, 0 is that empty element that you can add on both sides. And also you can have associativity, meaning that if I have 3 numbers that I add together, I can say A and B bracket together, or B and C bracket together. So let me show you what it means. So this is addition, I'm saying, is the OR combinator. Multiplication is the appending, adding stuff together. So, pop quiz. What's A plus 0? So I'll give you a clue because this is kind of tricky, but 0 is false, essentially. This is actually valid. This is actually valid Haskell, and I'll show you what that actually does to it. But the answer is A or false. False doesn't do anything, so it's A, right? So A times 1, again, the 1 doesn't do anything. A times 1 is not going to do anything, and that's the true kind of situation. 1 times A is 1. Now, multiplication doesn't have to be commutative, so we're fine. We didn't violate anything. A times 0, well, it just means you run the A, then you run the failure, right? Guarantee the whole thing's going to fail. A plus 0. Okay, but here's an interesting one. This kind of makes sense. A to the power of 5, because it's A times A times A times A times A. That will give you that. Right? And I'll show you examples of this. It's also distributive. A plus B times C is the same as A times C plus B times C equals AC plus BC. Yeah. So what's the problem? It's a number, right? But there's more. 1 plus 0, true and false, or false is true, right? True and false is false. And this, to translate this into something in terms of passes, this says try a 7, but it's not followed by an A. 4 not followed by a digit. Sorry, 4 or not a digit. No, this is an or. This is a minus, plus minus. You can look at this as 4 plus minus digit. Okay. You want to see it in action? Doesn't inverse, if you're doing an additive inverse, it's a semi-ring without negation. I'm sorry, without an inverse.
What was the question? Okay. They're not active inverse, so like P minus P is not zero.
No, I know, but it doesn't have to be.
Okay.
It's what's called a semi-ring. Some people call it a semi-rig, which means no negation. You don't. Yeah, it doesn't have a negative, so it's not a group. In fact, the requirement is monoids are, the addition is a commutative monoid, multiplication is a monoid, but not a group. A group has that additive inverse, you're right. Has an inverse for every option. Okay, so. So what that that means is it says try 1, which is always true, so it will be successful, right? Because it's true. So, but it doesn't do anything. It doesn't read pass any data. And this one does, A plus 1. What do I know? So that's fine, but if I put, that fails. So what it says is, this one, this will run A, perfect, and make sure the next one is not a digit. This one says, run A, make sure it's not a digit. Oops, got a 2, fails. That's a bit mind-bending, so don't worry about it. It's probably not something I use ever, but it's just kind of interesting. And it's kind of interesting that everything is passing the law, so it feels like it's right. And we also, as I said, we did pass the monad function alternative clause. There's also applicable clause.
This is only important because you actually implemented non-instance.
Yes. Yeah, so
so you basically turn it into a
yes. Yeah, and subject to those requirements that we see. Right here. So I did this is a non-instance. But there's actually more stuff you can do with it. So I have a version in there where it will, one of the things regex does really well is you can peek forward. Right? You can always do a zero width look ahead type of thing in regex, which means you're not consuming any stuff, but you go and check if the stuff is there or not. And that's easy to do because I have the state. It's not a problem. I have the string, the rest of the string, right? So I can always do that and reset the state. So I have that, but then the tricky part is, how do I go backwards? How do I look at the stuff that's already being consumed? So it turns out that's not too difficult. What you do is just add another string. So whenever you consume something, you put it into that other string. So your state is now a tuple. It consists of the stuff you passed and the stuff you're about to pass. And then you can always say, oh, I want to run the pass on the left one or the right one or something. So override it and then reset everything. But if you want to see that, I can show that afterwards. But I'm seeing you.
Is that the second item, the long one, the second item there, looks like you can expand algebraic expressions.
What was
You
it?
can expand algebraic expressions, algebraic.
Yeah, in fact, so one of the things that's really interesting is automatic differentiation. You've probably heard of that. Seriously cool. So this is, I have any expression, even a function, numeric function, and I can get a derivative, or multiple derivatives, or even better, symbolic differentiation. Not quite as fast, but the automatic differentiation is really, really fast. It uses something called dual numbers, and it means it keeps track of another number which holds the derivative. And that would be I think that would be a good tool for college to do. Yeah, so that's it. That's cool. Any questions? No questions. So.
You're gonna stay around, right?
Yeah, sure. Yeah.
Because I have a few questions, but I'm too embarrassed to ask.
Oh, I've left them.
Oh, no.
I'm probably not going to be able.
Let's stop the recording and